Good morning and welcome to Johnson Space Center and the STS-49 pre-flight crew briefing. I'd like to introduce first Captain Daniel C. Brandenstein, the commander of flight. Will introduce his crew and tell us about what they're going to be doing. Thanks.
Thank you, Barbara, and welcome to our briefing this morning. It's kind of early, so we'll keep it lively so you stay awake. It's obviously the first flight of Endeavour, and feel we're trained and ready to go and look forward to the mission. This flight is a little different than the flight sandwiched between. We've been flying space science missions. IML, LS, and USML is coming behind us, but this one's a little bit different vein, and that's space operations. We'll be going up and rendezvousing with Intelsat, which we'll talk about a little bit later. And likewise, we'll be doing a variety of operations that will help us better understand what it's going to take to the Space Station Freedom down the road. I'd like to start off by introducing the crew. First, the pilot on mission is Kevin Chilton, right here. He's from Los Angeles, California. We call him Chilton, so if you hear somebody referred to as Chilton, we're talking about him. He's a lieutenant colonel in the Air Force, test pilot, and this will be his first flight on the space shuttle. He's the pilot on the mission, and the pilots are generally the ones that keep the vehicle running, and our Jackson trade, he's also a backup arm operator of the ASIM operations, and he and I will be doing the lion's share of the work during the rendezvous. Next to him we have Keeb. He's a space engineer, originally from Jamestown, North Dakota. He'll be doing 2 spacewalks. He'll be on the Intelsat spacewalk and also the second ASIM spacewalk. And he's the computer expert on this flight. In fact, one of the laptop computers we're carrying has programming that he's developed over our training period to help us with various phases of rendezvous. And he'll talk a little bit about that later on. Next to him we have Bruce Nick. He's a lieutenant commander in the Coast Guard, a copter pilot from Clearwater, Florida. And he's the prime arm operator on this mission for all the arm operations. So he'll have a chance to talk to you about that a little bit down the road. He's previously flown on STS-49. I failed to mention that Rick Keep has previously flown on STS-39. Next to him is Pierre Hewitt from Fairfax, Virginia. If you look in his bio, he lists 2 towns. I didn't know how to handle that, so I just picked one. And he's a commander in the U.S. Navy, a naval flight officer. He's been through test pilot school and done test operations at the Patuxent Naval Air Station. He is the EVA on the same EVA with Rick. He's flying, going out on the first day with retrieve the Intelsat and do the work on that, and he's done a lot of work with the various folks getting ready for this Intelsat retrieve, and he'll be telling you a little bit about that. He also goes out the second day, the EVAs for the ASIM. He is pretty flown on STS-36. Next to him is Kathy Thornton, PhD in physics from Montgomery, Alabama. You hear anybody referred to as KT, that's who we're talking about. She will be doing the second EVA on ASIM. Her prime responsibility on this mission was getting our inputs and working with the various ASIM team members to bring that phase of flight together, and she'll be telling you a little bit about that in a few minutes. And on the far end, we have Tom Akers, Lieutenant Colonel in the Air Force from Eminence, Missouri. He's a flight test engineer, been through the Air Force Test Pilot School. He is on the same EVA team with Kathy in the ASIM, the first ASIM EVA, and he's also the one that's worked all the rescue equipment and procedures that we'll be using on this flight, and he'll tell you about that. He's previously flown also on STS-41, and I forgot to mention again, Kathy is flown on STS-33. So Chili's our one rookie, and the rest of us all have at least one flight under our belt. So with that, I'd like to hand it over to Kevin, and he can tell you a little bit about the rendezvous and the proximity operations we'll be doing.
Thank you. What I'd like to touch on this morning is just part of the unique parts of the rendezvous on this mission. We've done several rendezvous before in the shuttle program, but this one's a couple of unique features. The first one you'll be hearing about is a term called a control box, or control box rendezvous. Typically, when we go up to rendezvous with the satellite is quiescent. In other words, it's not maneuvering. It's been in its orbit for several revolutions around the Earth, for 3 days typically. The ground station had a good opportunity to track it. They know precisely where it is. They know exactly when to launch the shuttle to go up and achieve rendezvous. On this particular mission, we're going to do things a little differently. the Intelsat satellite is going to maneuver after the lifts off from the launch pad. That right now is in approximately 300 nautical mile orbit above the Earth. The space shuttle is going to launch into a 200 nautical mile orbit, and we're going to try to bring the two of them together. The whole sequence will begin immediately after liftoff. About 45 minutes after an engine cutoff, we're going to do our first orbital maneuvering burn, which typically puts us into our circular orbit on the Earth. This burn will be a little unique in that it will also be a rendezvous phasing burn. In other words, we're going to begin the rendezvous with our very first on-orbit burn with the shuttle. Meanwhile, Intelsat is going to begin a series of 4 critical on-orbit burns to lower it from 300 miles down to the 200-mile rendezvous area. Now, the spot in the sky that we've made it to come together is called the control box. Intelsat is required to be in that box sky 6 hours after the shuttle lifts off. Intelsat will be in that box, it will have engines turned off, and will be in its quiescent phase at that point, allowing the ground to track it several orbits around the Earth. When we wake up on day 4, the rendezvous is going to look pretty like all the other previous shuttle rendezvous will look. We'll just begin with our normal burns to come on in to bring the shuttle to close proximity with that. There's a few unique features, I think, come in close that are of interest. First of all, we're going to be doing the rendezvous. During the rendezvous final phases, Rick and Pierre are going to be out in the payload bay getting ready to capture the satellite. So during the final phase, when Dan is doing some of his burns to close into the satellite, these guys are going to be outside on during the burns and getting ready to capture the satellite. Another unique feature will be that we are going to be hot microphone in the rendezvous. In other words, the whole crew in the cockpit and the VA crew outside, whenever they speak, everything's going to be transmitted onto the ground. So typically on a mission, you only hear bits and pieces of conversations in the cockpit when the ground talks to the crew. This particular mission, anything we say in the cockpit, anything we say between the cockpit and the EVA crew, and anything they say to each other will come down hot to the control center. So I think that'll be an interesting part of the mission. You'll all be able to listen in and see exactly what we're doing as we come in. The last thing that's kind of unique about this is that we're going to be carrying some handheld lasers on board the orbit for this rendezvous to help us determine range rate as we approach the satellite. This will be kind of these are going to be used to eventually, we hope, to back up the shuttle's onboard radar. On this particular mission, it's just to evaluate the lasers, and Rick's going to go into a lot more detail on that. So the unique parts of our rendezvous are the control box, hot mic coming in, some laser operations, and having EVA crew members in the bay as we approach the satellite.
Okay, thanks, Kevin. Bruce Melnick now will give you a rundown of some of the RMS operations we'll be doing.
Well, as you can tell, this is going to be a complex mission right from the get-go, and it's going to be complex as far as the RMS or remote manipulator system is concerned. We have RMS operation planned for every flight day except for flight days 1 and 7. We're starting right off flight day 2 with the normal RMS checkout, and right after that we're going to go right into, and I say we, it's going to be KT and Chili and I. We're going to be the 3 arm operators, and we're going to take the arm into the payload bay and operate it around these different areas of the payload bay and see how the dynamics of the arm operates. Chili's already talked about the unique aspects of the mission. Well, we have a unique situation with our RMS in that we have no one training facility here on the ground where we can see the dynamics, see the geometry, see everything we need to see as far as how the arm operates in a zero-G environment until we get into space. So on flight day 2, after we do the checkout, the 3 of us are going to maneuver the arm around to different points in the payload bay, points that we plan to use during the ASIM Intelsat operations. On flight day 3, KT is going to take the arm and put it over the port side of the payload bay and observe one of our DTOs, our detailed test objective, which is our simultaneous wastewater and supply water dump. She'll be using the camera end effector of the RMS to observe any ice buildup and to monitor the dump as it's going on. We get into the meat of the RMS operations, of course, on flight day 4 with the Intelsat operation. First step in the Intelsat, or the first noticeable step, big step that we do, is we take Pierre on an elevator ride with the RMS and put him up into position, getting ready for him to attach the capture bar to the Intel satellite. While the arm is up in what we call the prox ops position, Pierre will actually be from his heels as you look at it from the orbiter, and Dan is the end effector camera on the end of the arm he'll use the cues that he sees in that camera for his final stages of the rendezvous and get the satellite stable in the end effector camera before we actually rotate Pierre up to attach the capture bar onto the bottom of the Intelsat satellite. The ground has helped us on this mission and making the arm operations as simple as possible. They have different ways that they can program in the computer and make it actually fool the RMS into thinking that it's going in different directions instead of with respect to the payload bay of the orbiter. One of these unique things that they've done on this flight is they've programmed a point of reference right at the center of Pierre's chest, so that once I rotate him up and he's getting ready to put the capture bar onto the Intelsat, he can give me voice commands, just move left, move right, up, down, and I can just put in one controller input, the translational hand controller or the rotational hand controller, and actually move Pierre right in the direction he wants to go without having to use coordinate movements. During the Intelsat operations, we're going to be using a combination of both manual flying, like I just described, and we also have OCASs, operator-commanded automatic sequences. While I'm doing the flying with the arm, KT will be staying one step ahead of me, program the OCASs as I need them to be ready to go on the next step. After Pierre puts the capture bar on the Intelsat, I'll of course go around and grapple the end of the capture bar, the end of the bar that he just put on, and then lower the Intelsat and berth it on top of the kick motor that we've carried up in the payload bay. After we've berthed the satellite, Pierre and Rick are going to tie it down. While they tie the satellite down and prepare it for deployment, I'll back the arm away and then do a P survey of the satellite to see if the satellite is in any damage or if there's any unexpected anomalies that may have happened to the satellite from the time it was launched to the time we've caught back up with it. Here again, the ground helped us out. They fooled the arm again into thinking that it's got an end effector that's 13 feet long instead of just a couple feet long, so I can simply back the arm away a couple feet satellite, put in a pure rotation, and with a nice circular arc around the satellite while this PV survey. So that'll end the arm operations during the Intelsat day. For ASIM, we're going to use the arm as a platform for both KT and Rick when they do their mass handling. They'll talk about that a little bit later, sure, where they're going to actually pick them heavy structure in the payload bay, and the arm will be their platform. They'll actually have their feet attached to the RMS and move these heavy structures around in the payload bay. We're also going to use the arm to do some fine mating of structures in the payload bay, and we'll use a varying degree and level of cues. I'll use visual cues, digital cues, oral cues from the EVA members, and we'll use a combination of those cues to see how close and how well we can dock different structures using the arms. And about the last thing we're going to do, we're going to use some automatic sequences to take the arm way up over the nose of the shuttle, and automatic sequences to take the arm way up over the nose shuttle and look at a couple of the spaced and freedom assembly positions. And we're going to use, again, the ground has helped us with this. We've got some automatic sequences that Kevin's going to be programming in. He'll be helping me out during the ASIM days, and we'll be using an automatic sequence, which is a little bit different than the OCAS that I mentioned earlier. The OCAS takes you from point A to point B without regard to what's in between, where the automatic sequence actually flies through pre-programmed points and pre-programmed attitudes and will take us up to space station freedom assembly position where the 4 EVAers can evaluate those positions. So you can see it's going to be a quite complex mission as far as the RMS is concerned, and I'm anxious to go ahead and get started.
Thanks, Bruce. Pierre was the crew's interface with a very large team that pulled together all the requirements to successfully do an Intelsat retrieve, and he'll tell you about that. Pierre?
Thanks. I guess I should start by saying it really was a big team effort. We had a good team. It started, as they mentioned yesterday in the briefing, I think talked about it, a couple weeks right after Intelsat had its problems. And they put a team together, and everybody worked real hard together. JSC, Hughes, Intelsat, just everybody just did a really great job getting it all put together, and I think we got a really good mission plan. We've tried to cover all the contingencies. That we played the what-if game 100 times, and we've tried to think of what if this happens, what we're going to do. And I think we've done a real good job getting ready for this mission. Let me kind of give you an overview of what we're going to do, what Rick and I are going to do out in the payload bay. As mentioned, when we are in the final phases of rendezvous, Rick and I will go out the hatch and we'll start getting the work site area prepared. On the end of the arm, Bruce will take me up into the poise for prox op position. While I'm doing it, Rick will be preparing the adapter ring. Several pieces of the hardware on the adapter ring be prepared for the actual mating. Bruce described how we'll put the capture bar on. After I get the capture bar on, I'll hard lock the capture bar with power tool, and then I'll stop the rotation using the steering wheel, hopefully stop it nice and still so that it can go in there and grab it. I guess another unique feature I should mention about this is this will be the first time we've ever used the PAD, the PFR attachment device. PFR is portable foot restraint. Unlike previous missions when we've had a person on the end of the arm, we've used a foot restraint, which actually goes into the end effector of the arm and takes up that place where we normally grapple satellites. Easy for me to say, right? But we have a device that was actually designed by an engineer in Houston at JSC that actually fits on a part of the arm that leaves the grapple fixture open. And what that allows us to do, not have to take the 20 minutes or so that it would be required to take the manipulator foot restraint out of the arm, stow it, and then have the arm go back up and grab the satellite. So as Bruce mentioned, once I get the bar on and stabilize, I'll be able to just take on for the ride as he goes in and grabs the satellite, which should only take 2 or 3 minutes. So it saves us a lot of time, saves us some fuel as far as proximity operations. Well, after Bruce gets it grappled and he gets it down on top of the satellite, we'll do a few other things to get the satellite ready for the mating. Rick will pull the shower cap off that was described yesterday off the satellite. Bruce will bring it down and make 2 elements. And then Rick and I will go to work underneath the spacecraft in foot restraints, mating clamps, umbilicals, releasing push-offs, and basically all the activity to marry the 2 pieces together so that we can deploy this thing. Once we get it all married, we'll then start taking the capture bar apart. I think this was described yesterday a little bit. We take the right beam extension off, the left beam extension off. We've already taken the steering wheel off. And then we actually take the capture bar and release it from the satellite and lower it down on top of the adapter ring. And the reason we're doing all that is, number one, is to reduce the weight of the capture bar that actually flies uphill with the Intelsat. And at the very end, when we're all done, since the capture bar will be attached to the adapter ring, that when Intelsat burns their motor and then they separate from the motor, there will be nothing on Intelsat that we put on there, because everything will still be with the motor, and so they'll have basically the same weight spacecraft they came to us with, minus the fuel they used to get up to orbit. Once we get all the things married and the capture bar taken apart, we'll go through a pretty extensive deployment check to make sure the work site is clear of all the hardware, that there's not going to be anything in the way of deployment. We'll power the stage and boost units and turn on the timers, and then Rick and I will retreat to the airlock, and Kath, who will be doing the deployment, will actually fire up the switches to deploy the satellite. Once we complete that, Rick and I will go back out and reconfigure some foot restraints and basically do some cleanup to just get the payload bay ready for the EVA, and the next Kathy and Tom go out. That's it.
Thanks, Pierre. For ASIM, or Assembly of Space Station by EVA methods, Kathy was the crew interface with the team that pulled that all together, and we'll let her tell you about that.
In ASIM, we're not testing space station hardware. We're developing EVA techniques, which will help us to build the space station. We have a number of objectives that I'll mention in no particular order, one of which is to demonstrate the ability to perform 3 consecutive EVAs. That's a requirement for station assembly and also for the Hubble revisit next year. The stowage for EMUs and all the associated hardware and the training load we have put on the facility here has already been a challenge for JSC. We're going to evaluate EVA fine positioning and installation of a large mass, the MPES pallet, which has been transported to the work site by Bruce in the RMS. And that's analogous to the installation of the control moment gyros and the mobile transporter batteries and some other orbital replacement units on station. We're going to develop techniques for the EVA crew members to give verbal guidance to the RMS operator, and that will allow Bruce to position the pallet much more precisely than he could using only payload bay cameras and directing out the window. For some space station assembly sequences, the arm operator will be required to position objects in places where he does not have direct viewing and probably limited camera viewing. We're also going to demonstrate the ability to use our helmet-mounted cameras to give him some kind of viewing of the mating of the pallet and the structure. We're going to evaluate the EVA working conditions in the space station assembly area, which is forward and above the cabin, forward of the nose. In particular, we're going to look at lighting, communication, the EMU thermal conditioning, whether we get too cold, too hot, direct viewing, and also camera viewing from the payload bay. We're going to look at the -Z star tracker, which will be partially blocked in one of these positions, and see how it operates with field of view partially obscured. We're going to do some EVA handling of a large mass, the MPES pallet and the pallet attached to the fixture. We're going to remove it, transport it standing on the RMS to somewhere above the payload bay, move it in directions, and see how that feels. That's a larger mass than we would normally plan to move, and we think that will station a few more options of how to move around equipment when a grapple fixture is not available or the clearance is not available for the arm, or for whatever reason they can't use the arm. Another one of our objectives is to evaluate some crew self-rescue concepts Tom will talk to you about. On Flight Day 5, we're going to do the first ASIM EVA, and that will be Tom and me. And major blocks in that EVA are fixture assembly, build up half a bay of truss using the earlier station configuration of sticks and balls, struts and nodes, and EVA joints that were developed at Langley Space Center. We're going to do the MPES mass handling, just the MPES pallet alone with a steering on it. We're going to take it up above the bay and move it around, bring it back down and put it very gently and carefully into the Perlas. Tom is going to do an evaluation of a crew propulsion device, which he'll talk about. We're then going to use two methods to attach the MPES pallet to the structure that we built. It's really the only reason to build this structure. It's no longer a space station equivalent, but we're building it as a fixture to attach things to. Bruce is going to bring in the MPES pallet to different levels of precision, and we'll see how much of that we can take up EA and how well we can talk him into the fine positioning. We're going to then go up to the space station assembly area, forward to the nose, and do some representative type tasks. Again, this is not station assembly, but while we're up there with the MPES pallet, we'll be riding on the arm, and the arm will be carrying the MPES pallet. We'll disassemble the legs that we put on there and stow them and get it ready to come home. We're going to berth the MPES back in payload bay using the helmet-mounted television camera. Bruce is going to use that as his cue to get back in there, evaluating what station might to do if they needed to do some RMS work out where there are no cameras, that we could take one of these EMU cameras out and leave it perhaps, and they could zap. Then Tom will do a couple more crew self-rescue evaluations. On the third EVA, ASIM 2 and Pierre are going to go out. They're going to start off with two different methods of mating the pallet to the structure, which was up overnight. Then Rick is going to handle the MPES with the fixture attached, which is roughly the same mass as the MPES own, but it's a larger volume. And it's different attachment points farther from him that he has to hit and brings it back down. They're going to go to the space station assembly area, up and over the nose, and the same task we did, but with varying lighting. We'll try to take down the payload bay lights one at a time and see when they're uncle. They'll also do some crew self-rescue evaluations. They will berth the MPES back in the payload bay, this time using just verbal guidance. They'll talk to Bruce and they'll tell little right, little left, or port or starboard, up or down, and yeah, towards me, and get it back in the payload bay. It will then take down the fixture that we built, and at that point we'll have everything stowed in its launch configuration and be ready to come home. They'll have a couple more crew self-rescue evaluations, and then we come in and clean up and get ready to come home in a couple days.
Thanks, Kathy. Kathy's alluded to the area that Tom spent a lot of time working on, and that's crew rescue, also something that we feel important in the space station assembly era, and we'll let Tom tell you about that.
Well, as you all know, when we're out VA nowadays, we always stay tethered when we're out in the payload bay. And if for some reason we would become tethered and float away from the space shuttle, always treat our commander and pilot very well, because we'd like for them to fly over and rescue us if that was to happen. We get Space Station Freedom operational in a few years. There's times when we're out EVA as crewmen, and we have the shuttle around to come rescue us if that was to happen. We would become untethered or a tether was to break. One thing that we want to look at is possible solutions to that problem and how we would effect a crew self-rescue during the Space Station Freedom times when the shuttle is not around. And so the crew and thermal systems have come up with 5 different types of hardware that we're going to evaluate during our ASIM EVAs on this mission. All of these are concept type evaluations. In other words, we didn't spend a lot of extra money making sure the packaging was as you would expect it to be for a crew self-rescue device. So probably your first comment when you see us doing these evaluations during our EVAs and ASIM is going to be, well, my goodness, that's too big and bulky. They could never carry that around during an EVA. And that's exactly the idea for this, because we tried to use as much off-the-shelf hardware as we could, again, just to evaluate each concept and not worry about the packaging and the deployment of each of these devices. Of the 5 devices, 4 are what you would call grapple-type devices. In other words, if you became detached, you would deploy one of these mechanisms and reattach yourself back to Space Station Freedom. One of those is just a simple 20-foot rope that we would toss and we would wrap around a section of the Space Station Freedom. We call that the Astro Rope. The other 3 are pole-type devices. One is a mechanical telescoping pole. It's like a radio antenna, and we call it that, the TP or telescoping pole. It goes out to about 12 feet. Another second pole-type device is actually an inflated pole, and we call it the IP, and it is cloth-type Kevlar material that will, with compressed gas, inflate to about a 2-inch diameter and go out again to about 12 feet. Each of these devices, the grapple devices, have an end effector on them that we can hook onto some part of the Space Station Freedom. Now, on our mission, we're going to actually just use handrails and tucks in the payload bay of the Space Shuttle. The third grapple device is an electrically powered pole. Actually, will go out to 20 feet in length, and we call it the I-stem pole. The 5th crew self-rescue device we're going to look at is not a grapple-type concept at all. It's a propulsive device, and you'll probably recognize as a redesigned old handheld maneuvering unit from Gemini and Skylab days. We have gas bottle packs that we strap on our back, and we just have a hand-held wand with nozzles on it that we put in certain positions that will hopefully be able to let us, if the type of rotation that we want on our body, to stop any rotation that might have when we become detached. Now, each of these, as I mentioned earlier, are all just concepts, and each of them have limitations, not only just in packaging and how we would carry them, but each has a limitation in the concept itself. For example, all the grapple-type devices that you would reattach yourself with would, number 1, require that you can see a target, and probably number 2, that you don't have very much rotation rate on your body so that you could deploy it. And of course, that limits the envelope that you could use those in. The crew propulsive device, with the old handheld maneuvering unit redesigned, or CPD, is actually probably the limitation we see there is how much propellant we have. Once we stop our rotation with it, which is its primary design, we don't have enough propellant probably to translate all the way back into Space Station Freedom. So we're going to be evaluating all of these, and what's kind of nice about them is all of them can be evaluated in a fairly short period of time. As Kathy mentioned, during the EVAs, you'll see these interspersed during the ASIM activities, and we've tried to construct that timeline so that we're doing these evaluations when Bruce is repositioning the RMS through ARM, and so we take up all of that dead time that we would just be waiting for the ARM to reposition by doing these type of evaluations. And hopefully, again, as I mentioned, looking at these concepts, we know that any one of them at this point is probably not going to be the answer, concept itself, or especially the hardware, for what we come up with as a final design. We hope to learn enough from looking at each of these concepts to at least improve and maybe come up with a good solution to the crew self-rescue problem when Space Station Freedom becomes operational.
Thanks, Tom. Next, Rick, about the photo TV and also the laser work we're going to be doing. From this mission, the lion's share of our data collected will be done through photo documentation, and we'll let Rick tell you about that.
Kathy talked about the fact that one of the requirements, we're trying to understand how we can do 3 spacewalks in 3 days and 4 people, which means 4 spacesuits down in the middeck dashed away somewhere, plus our 7 pressure suits that we wear on ascent. And immediately, if you've been through the orbiter at all, if you looked in some of the mock-ups, 7 bodies, 7 pressure suits, 4 spacesuits, you can see that we have a volume problem. And it's one thing for us to come back and talk about how crowded it was, but what we really want to do is come back with some pictures and show how crowded it was, partly, and also how we attempt to solve the problem on orbit. And so, in addition to that, we're going to do all this preparation. You know, we have, in the airlock, there's room for 1 spacesuit on each wall, basically, and they're hooked up to Orbiter 02 and so on, and go in there and get ready for an EVA. We're going to launch this orbiter with 4 spacesuits in the airlock, 1 on the floor as well, and 1 on the ceiling as well. And for each EVA, we have to reconfigure the airlock by moving a couple of them out. First time it'll be Pierre and I will put our suits on in the airlock. After that EVA, we've got to get those out, recharge them, get them ready for the next EVA, the next spacewalk, and then bring Kathy and Tom's in, get them ready to go. Next day, shuffle it again. So what we want to do is record all this on film, and I sort of volunteered for the photo TV job after my last flight because the first time around for me, my focus was on getting the science done, getting the job, that we're all set out to do. And one of the things I realized after the flight was I wasn't entirely happy with what we came back with photo TV recorded-wise. I didn't feel like we could really tell the story very well and demonstrate what we did in flight. So I said, to handle that, it's something of a jigsaw puzzle, I think. We put them up the other day. We have 21 different kinds of cameras on board. And to talk about that a little bit, we've got the usual 6 cameras out payload bay. There's one at each of the corners of the payload bay, and then 2 on the arm. One up by the elbow of the arm, one on the end effector of the arm. So that's 6. We have an additional payload bay camera on this flight, a keel camera, which is mounted just in front of the Intelsat cradle, which is bore-sighted right up the -z axis. It was initially put on to help with the task of berthing the Intelsat onto the motor, but in fact, as we've gone along in getting ready for the flight, we've come to realize it's probably most useful as a rendezvous prox ops aid because it gives Dan a point of reference out in the payload bay. When you're flying a rendezvous looking out the overhead window, you can fly straight up the satellite. The only problem is you keep the satellites out the overhead window. That's not as good a place to have as out over the middle of the payload. So this camera will help Dan do that job. So that's 7 cameras out in the payload bay. Additionally, Pierre and I on our EVA and Kathy on their EVA will each wear an Emu television camera. The EMUs are color cameras, and they're real interesting to watch the view from them. We've used them on earlier flights, not so much recently. We use them against flight. The downside to watching is you'll get a chance during the flight is that you look at whatever we happen to be looking at in whatever orientation we're looking at it in, and so if we start moving around like this, back and forth, the camera's going crazy, and pretty soon your kind of eyes are rolling around, and so managing that is going to be kind of interesting. We also, inside the orbiter, have some TVs. Carry a spare TV camera, which is just like the payload cameras that we can change out if necessary. We also are carrying 2 camcorders now. We've tried to go toward more off-the-shelf use of hardware to keep costs down and so on. We're carrying a couple of off-the-shelf camcorders, and those camcorders are going to do 2 particular jobs with them. One, we're going to have them one of them going to be set up down the mid-deck, all the lights that we can get, to record all this fling of spacesuits in and out, back and forth, plus kind of demonstrate crowding effect. Now, the problem with showing crowding in the orbiter is one that you're probably aware with a wide-angle lens. No matter how crowded it is, it doesn't look crowded to use a wide-angle lens. And whenever I've shown friends through an orbiter mock-up, the very first comment invariably is, "It's so small." It's just like the comment when somebody goes to the MCC, the control center, for the first time, say, "Man, I envisioned such a big room, but it's so tiny." But we're going to film it anyway, so at least have it recorded. Likewise, up on the flight deck during the rendezvous, we're going to set up a camera up on the forward part of the flight looking aft and try to capture all of the activities in the orbiter during the rendezvous, with Dan flying, with Chile up in the front, controlling the orbiter systems and worrying about targeting and all those kind of things. Bruce in the back operating the arm, Kathy operating lasers and television cameras, Tom being out with television cameras and being the inside the orbiter EVA controller. We call him the IV person. But Tom's job is to be inside the orbiter, making sure Pierre and I are following the timeline, because we don't have a checklist out there. And how we do business, we like to do every step by the checklist. Invest years into developing checklists that have everything listed. And normally we like to make sure every single step is done. Well, when we go EVA, we can't bring that checklist out with us. Tom is there to make sure that we do all the steps that are listed in that checklist. So all these people are scrambling around in the orbiter trying to get all these jobs done. We're going to record that on the recorder. We've got a 16mm movie camera, and we hope to record as much of this as we can with the 16mm movie camera. We've got 2 35mm cameras that we'll take out in the payload bay with us. We'll have one, we won't really carry them so much with us, but we'll have them to go get when we want to take pictures of something. One of the things we had to worry about here is you can't change film out, of course. When we're out, it's basically, they're off-the-shelf 35mm cameras. So we loaded up one with day film and one with night film, and we'll go get the right camera depending on whether it's daytime or nighttime when we're trying to take our pictures. Inside the orbiter, we have 2 more 35mm cameras and to take still shots. In addition to that, we have 2 70mm cameras primarily for Earth observations, but we'll also be doing some payload bay pictures because of 70mm, you get a little larger format. One other primarily Earth observations camera is a Linhof camera, and I'm not sure if any of you are familiar with it, but it's a much larger camera, and you put it all together, it's about this long, about this big around, weighs quite, although in orbit that's not such a problem. And it's a terrific camera. It's got a vacuum pump to set film down flat. We've used it for a lot of flights, and it brings back terrific Earth observations photos. The other unique camera we're flying for about, I suppose, the 3rd or 4th time is an electronic still camera. Instead of a film plane, it's got a set of ECDs. What's that even stand for? Chargeable device, I guess, yeah. And the camera, pretty high resolution, much higher than a camcorder. And our objective here is to try and take some pictures, particularly if it turns out that Intelsat's got anything out of configuration. We want to be ready to get some high-resolution pictures, and we can actually get these down to the ground very nearly real time. Within just a few minutes, we can take the picture, ship all the 1s and 0s down to the ground since it's all digital, and and they can make a print of that so that people on the ground can look at the problem and analyze it and try and come up with solutions. So that's another camera we're going to try and take pictures. Now you can kind of picture what's going on at the rendezvous. You know, we've got people flying the orbiter, flying the arm, watching the EVA, and at the same time trying to manage cameras, and so we put together a pretty complex photo TV plan that lists hopefully what camera we'll be able to use during each phase of all these rendezvous activities and spacewalk activities. The second thing I want to talk about besides photo TV has to do with, more to do with rendezvous. Now, you might say, why would I have anything to do with that? I'm going to be out in the payload bay. Over the years, as some of you are familiar from STS-49, I spent a lot of time working rendezvous. I started here at NASA as an engineer working rendezvous procedures in '79, and I've kind of kept my fingers in it ever since. And one of the things that's always been of concern to me as a procedures person and as a crew person is that when we get inside about 100 feet, the radar drops out. It just can't, you know, it's the way it's designed, it can't lock onto a target inside of about 80 feet. So from 80 feet on in, the proximity operations task is absolutely only out the window. The guy in the orbiter has no tools to help him, nothing telling him range or closing rate, any of those things. So it's strictly an eyeball test. And I've always wanted to try and get the pilot something to help him do that job. And over the years, we tried a lot of things. We try with payload bay cameras, triangulating. We point them both at the satellite, look at tilt angles, and figure out, okay, it's 60 feet here. We must be this far. Try and take that, several marks, turn it into range rate, and so on. It gets to be a complex task, and the cameras weren't meant for that, so they're not particularly accurate. As Dan alluded to earlier, I wrote a computer program to try and help with that. On one of our laptop computers, you can put in camera angle. It'll actually draw a picture of the orbiter and draw a trajectory. It takes a couple of data points and figures out where you must be going. That's pretty good, but it's still not, you know, not something I'm completely happy with. And this flight, we're trying something new with the lasers that Kevin talked about. There are 2 of them, and once again, we tried to get as much as we could off the shelf, and I brought them along to show you today. This one is actually a police laser unit. It gives you output in, normally for the police it'd be in miles and miles per hour. We made a slight modification so the output is in feet per second. Now, you don't have to worry because these things really are eye safe. Let me see if I can bring it up. No, they're eye safe, really. I can't make it turn on today. You can take them off. I can't power this thing up. I don't know what's going on. We added a serial communications line that goes from this laser to the laptop computer, so that Kathy's looking out the window at the satellite and fires off a mark. Automatically, the data gets sent over the line to the PGS or our laptop computer. That'll get recorded. Also, Kevin will be running that computer along with his other tasks, helping build the trajectory so that Dan can look at the picture every now and then and see how it compares to what he's seeing out the window. it also be recorded for post-flight analysis. The analysis guys can go look at the marks that were taken with the laser, compare them to what the ground track and everything else thought was gone, and figure out how well the laser performed. During the rendezvous, we'll be taking marks with this guy, comparing against the radar itself. We've also got another laser on board. And when I had this home the other day, when I was doing a little training with it, my daughter said, "You've got a G.I. Joe thing, Papa. Why is that?" And in fact, again, this came to us basically directly from Desert Storm. It's a military piece of hardware. It's another laser, and it's a pretty simple operation. You turn it on, charge up the capacitor, and fire it off. The downside to off-the-shelf hardware that's literally off-the-shelf like this one is that this outputs the information to us in meters. Everything else we do is in feet and feet per second, so we have to have a little bit of conversion help to get that information over to the units that we're comfortable with. This guy we expect, and this also doesn't output range rate, it's just range, so you have to get a couple of range marks and figure out from that what the range rate is. This one we think is probably going to be good out to several thousand feet, and a T-38, we've taken these out flying, and we've gotten marked as far away as 1,000 feet with this guy because it's pretty powerful, but the orbiter has a lot of windows and a lot of coatings on the windows, so we're not sure what the range is going to be on this guy. This one in the 38 is good out to a couple of thousand feet, and it was actually tuned a little bit to try and get at the right wavelength to make it through the orbiter windows with the least loss, which turns out to be about 50%, by the way, so it's still pretty significant loss. We expect it to be up to a couple of thousand feet, so we'll use this one at the longer ranges, a couple of miles on in when Dan starts flying manually, and then switch over to this inside a couple thousand feet, and then assuming everything is going well, you'll be able to turn the radar off at a couple of hundred feet out and be able to trust this for range and range rate information from there on in. And that's all I had, Dan.
Okay, great, thanks. The other thing that's happening on this, obviously, it's the first flight of Endeavour, and its original test flight. A few of the new things that will be on board, I think you're probably all well aware of the drag chute, which is probably the one new item that's big and visible. In addition to that, to be the first flight with redundant nose wheel steering, and between the drag chute and the nose wheel steering, we're adding a significant margin to our go for the landing case. And now that we're going back as often as we can to the Kennedy Space Center, that extra margin for landing on the runway down there is something we've been looking forward to. The other new items we'll have three new APUs. One of them flew on Charlie Bolden flight, so we got the flight on one of them, but our vehicle will have three of them. We'll also have two new TACANs, a new and different type MU, a new and different star tracker in the -Y star tracker position, and it'll be the first flight of the new software drop OI-21. Once again, the big change in OI-21 is the automated continuity aborts, and we hope not to test that. That's pretty much a rundown of what we're going to be doing on this flight, and I said trained, and we're very comfortable. We've had a good training that's done an outstanding job of getting us ready, and it's been a lot of work filling this all, because with two different crews doing EVAs, we take up the lion's share of the time in the water immersion facility, so we've been doing a lot of work on that, but right now I feel comfortable that we're ready to go fly, and as soon as we have a real launch date, we'll go down and do it. Barbara?
Thank you. We'll take questions now here at JSC. Please state your name and affiliation. Marcia?
Could you give us some sense how much more work, training has gone into this mission than previous missions, given the fact that there are two EVA crews?
Well, I can hand that off to Pierre or Kathy or the people doing the EVA. That's where the big timeline is the amount of time they've been in the tank, and they can give you a rundown of that. From the whole crew standpoint, what it's done, it's kind of kept us divided. The EVA crews are off doing their training in the tank, while the orbiter crew, Chili, myself, and Bruce, are off in other facilities training for rendezvous and arm operations and the like, and we can let Pierre mention the amount of what-if training they had.
Well, it's probably obvious to you if you're doing two crews doing EVAs, it's probably twice as much, and that's what I probably guess is about twice as much EVA training, because we have two separate crews we're trying to train. In addition, we didn't mention, Tom is trained as Rick's backup on Intelsat. Rick's my backup on Intelsat. So if I have a bad meal the night before and I don't feel too the next day and I can't go out, Rick can jump in and do my job. Tom can That's an idea. Wait a minute.
You probably cook for yourself that night.
I'll cook for myself that night, right? But anyway, so there's quite a bit more training. STS-37, the last EVA we did, one of the things Jerry and Jim talked to us about afterwards is one of the things you need to do as you start getting close is do lots of runs, lots of long runs, 6-hour runs for conditioning. So we're similar to them in that respect in that for the last 2 months or so we will be doing at least 1 run a week, each team in the wet up 6 hours long for conditioning. We've pretty much got all our procedures down and we really have the timeline down real well. Now it's just a case of maintaining that conditioning that you get from working in the suit for a long time. So I'd say it's probably about twice as much as what we've done on previous missions.
Mark?
Mark Carreau, the Houston Chronicle. Could you touch historic, and I don't really have one person to ask about this, but previous rendezvous and spacewalk satellite repair missions, maybe you could sort of draw historically on a few key points that your mission builds on or you looked at for background to plan your activities. And I think you touched on the Hubble and the Space Station build, but are there some other missions that this sort of lays some groundwork for?
Pierre,
I guess I'll answer that one.
he can talk at least because he went back and researched a lot of what had been done previous ones to help us develop some of our procedures.
When we first got started way back in March of '90, we looked at all the previous rescue missions, Westar, Palapa, LESAT, and SYNCOM, or SolarMax, and we took a look at all the scenarios. And of course, Westar and Palapa had nozzles on their satellites that we could stick a probe into. Well, this satellite didn't have that one, so we kind of had to take a different approach. But we looked at all the information that was available. The technical people did. We also got all the crew reports out and reviewed all those things. So we've done our homework in that respect, and we've tried to use those types of things to help us plan for this flight, plan for the unexpected things that might occur. We even had Joe Allen, who was a Westar Palapa astronaut rescuing that thing, come over to our mass simulator, which I think you're going to see this afternoon, and had him get on there and wrestle with our satellite simulator to see what it feels like. And we were hoping he would tell us that it feels like a satellite, and that's what he did. He said it's a pretty good simulation of what a massive satellite feels like in space. So we've tried to draw on all that history and that experience to build our hardware and to give all the what if this happens and what if that happens type of things. So.
I guess one other comment along those lines is that basically all those other rendezvous EVA combinations that Pierre alluded to did it more or less exactly like we're doing it. Rendezvous more or less first thing when the crew gets up on rendezvous day, jumps right into the rendezvous. The EVA starts sort of midway in the day and goes, till fairly late. It's a maximum length crew day. It just barely fits, but they fit it in, and we're fitting in pretty much the same way that they did.
Tony?
Tony Clark, CNN. Commander, I'm curious, during Dan Golden's confirmation hearing, he said one of the things that needs to do better is explain to the public why space missions are. How do you think this mission falls under that?
Well, hopefully with the briefings you had yesterday and what we're doing today, we're explaining what we're doing and why. And I think one of the things that PAO came to us with, and that was Chile alluded to it, that we're during the more intense part of the mission, the final phase of the rendezvous and the early capture phase, we're going to attempt to go what we call hot mic, so you can hear everything that the crew is doing. And we've tried this in the simulation, and it's worked fairly well. It conceivably could become unbearable and undoable, and we have to break it off. But our going-in positions, we're going to give it a try, and hopefully bring you folks and anybody else that's listening into the cockpit and letting you see what's really happening and what's going on. Hopefully, in fact, we're going to sit down with some of our PAO commentators to talk with them and fill them in, because in that environment, obviously, we're going to be talking a lot of jargon and a lot of shortcuts, because trying to get all that conversation into a little space. So probably the average person on the street, it's going to be Greek to, but hopefully someone that's done a little bit of research with it will be able to follow what we're doing and understand what's going on.
Do we have any other questions here? Then we'll go to NASA headquarters for questions.
Hi, this is Craig Cavalt with Asian Week. Two question areas, I guess. First for Dan, can you take a minute to discuss the inertial fly-around phase that you're up close to the Intelsat. And then, I guess, for the whole EVA RMS team there on the Intelsat capture aspect, can you describe any unknowns you might face on Intelsat attitudes and rates between the orbiter, the arm, and the Intelsat, how that might end up changing the plan a little bit?
Okay, well, I'll talk a little bit about the phase, the inertial approach. The Intelsat is stable relative to the universe, or the sun for this case. They need the sun angle coming right. So as it goes around the Earth, relative to the Earth, it essentially does one tumble in one revolution. When we come into daylight and see the satellite, we put the shuttle into what we call inertial. So the shuttle using the same reference that the satellite is in. And we hope, if our timing and the rendezvous goes correctly, that will have it positioned, oriented in the way we would like it relative to the shuttle also. We will do the final phase of the approach with ourselves in an inertial hold and the satellite in an inertial hold. Then we get up real close and get it in the end effector, as Bruce indicated. It's about 35 feet away then, and we'll stabilize it there. And that's where we make our final decision on whether or not we have to tweak up attitude or anything. And what we're looking for is positioning the end of the satellite that Pierre is going to be attaching the bar to in such an orientation that Bruce from the cockpit can see more or less what he's doing to help him operate the arm. Also orients it the way we've been training relative to the payload bay cameras. So we may ultimately end up in close doing a bit of a fly around just to tweak up that attitude. But from my previous experience, the guys on the ground do a real good job of getting us to the right place in time, and I don't expect to do much of a fly around. And the other part of the question?
I think when Dan leaves it off, it'll probably be so rock solid, we probably won't have to worry about a lot of RMS maneuvers or a lot of maneuvering me. But Intelsat's going to have it go down to about 0.65 RPM, less than 0.7. And we've trained with even higher rates, so we're not concerned about even if they can't get it down there. But they're also going to get it down there. They're going to tell us what the rate is, and the guys inside are going to be little calculations with a stopwatch to tell us what the rate is. So the revolutions of the satellite is not a problem. And then because Bruce has this payload ID mode he was telling you about earlier, he can just position me basically with my left-right commands to get right in place to put the bar on. And we've done quite a bit of training over at the mass sim that the folks here will get to see later today, trying to develop those procedures. Did we answer your question, Craig?
Yes. Another question on the crew propulsive device, the little gas gun. You might want to discuss, I guess this is probably for Bruce, or Tom there, discuss the exact profile you put the gun through in terms of stabilizing attitude rates. You'll get going and see if it'll damp it out.
Okay, our plan is, since before we actually try to see if it would recover from any sort of rates on our bodies with this, is to check out the positions that we put our hand in to effect a plus or minus yaw, pitch, and roll. And the crew and thermal systems folks came up with these hand positions, and we've trained to them. One of the problems is we don't have a real place down here to train to see how well these are going to work. We've done some work on the air-bearing floor where we can see what happens in one axis. We've tried to spend a lot of time in the KC-135 and zero-G flight, but that only lasts for about 20 seconds. Of course, the airplane motions, you really can't tell what you're getting out of the gun and what you're getting out of the airplane a lot of times. So we're going to put it through a real disciplined set of maneuvers just to make sure that the hand position's trained to give us what we think they will. And so we'll go through a plus or minus yaw, pitch, and roll. Then we'll try to do a short translation forward with CPD. And then finally, we will do a push-off and try to some rates into our self in multi-axis, and then see if we recognize what those rates are and go to proper hand positions and stop those rates.
I guess one comment on the push case where we give ourselves rates. The tethers, which are our tenders, and we always keep them on, in this case almost create a little bit of a problem for us because we can't just arbitrarily go tumbling off or we're wrapped up in our tether before we get a chance to evaluate the propulsive device and its ability to slow us down. So it constrains the task a little bit in that respect.
Now we'll go to Kennedy Space Center for questions.
This is Todd Halverson of Florida. Today, Tom Akers touched on it a little bit, but I'm wondering if maybe Dan can elaborate on what the contingency plan is for if the EVA crew members gets tethered and goes float up in space?
Okay, as Tom mentioned, anytime we do an EA with the space shuttle, we keep reserve propellant on board for that eventuality, and that's one of the reasons doing this test, because we don't have that capability in the space station. But we have some procedures depending on which way they're going, and we essentially just the final phase of a rendezvous, and anytime we have anybody out EVA, either Kevin or myself is at the aft station where we can take over essentially immediately and fly to the position where the crewman is. One of the parts of this flight that are a little unique is that we have the EVA crewman way up over the nose, where normally we don't do EAs. And we've developed some rescue procedures there. Well, first of all, when we have them up over the nose, we inhibit the forward-firing jets, so there's no chance that they're going to get blasted with an RCS jet. And that limits our capability a little bit on the vehicle. However, we have the tail jet activated, and if a plane should get free up there, we can pitch nose down using just the aft jets, and that's probably what we do, start the nose to pitch down a little bit, and then we translate forward. In other words, we can move forward and get them back over the payload, and then quickly reactivate the forward jets, and then we're back to the normal primitive flying configuration, and we just fly them into the payload bay and let them grab a hold of something.
Ocean Earth News and via satellite. I guess for Pierre, we talked a while ago about the SAT. What concerns do you have that it was an expendable vehicle with NASA safety over every bit of its launch, precision preparations for launch?
Well, actually, the SAT originally was designed to be flown aboard the shuttle, so the Intelsat 6 series of spacecraft, I believe, all went through the NASA payload safety review cycle. And in addition, for this mission, it went through that whole process, and Harold Battaglia's group, who does all that, did a superb job of evaluating all the hazards and making sure that all the hazards or any hazards were controlled, and all the proper safety measures were in place. So I don't think I really have any concerns about that. I think the safety team here at JSC with Hughes and Intelsat did a superb job of looking at all that stuff.
For KT, back in 1984, when Kathy Sullivan made the first female U.S. EVA, there were concerns that because of the body fat difference between men and females, that she'd have to start her pre-brief period much earlier than Dave Leisman would have to. And I'm wondering if that's the same case now, or has more research been done?
I don't think we've had any more research, but we, in all the chamber runs we have done, that we personally have done, and I guess there have been chamber studies with women, they've not found any difference that I'm aware of in the incidence of bends due to body fat. And I'm on a diet.
Well, I hope so, if you're going to become the world's greatest weightlifter up there. And for Rick, even though you're going to be out in the cargo for this, but will somebody be operating the ESC during Intelsat EVA, and will we be getting a live downlink of the ESC shores as it happens?
Well, I think that's a question. We intend to take some pictures. If it turns out that we do, in fact, have acquisition, if there's a good KU-band comlink. Of course, you got to remember there will be no KU-band comlink while we're using the KU-band for radar. So until we stop using radar, there certainly won't be any either TV or electronic still camera stuff coming down. Once we drop the radar, we're going to be trying to take pictures and send you what we can. But again, I have to reiterate that we have a real problem inside the orbiter as far as crew time available go, because we've got a limited number of bodies trying to do an awful lot of things, and furthermore, there's only a couple of windows back there, and they're smaller than the people are. And so just getting to a window with a camera for a task to do something that is, in a sense, not required, it has to be managed. And we're not going to promise anything about what will be coming down from the electronic still camera, but I think you can count on us to do our best to get some pictures and get them down as close to real time as possible.
This is Irene Brown with Florida Today. Bruce, you mentioned that you're going to be doing a survey with the cameras before any grappling, or actually before there's any repairs to the Intelsat. I was wondering if there's any contingency plan to bring the satellite back to Earth if you find anything that can't be repaired.
Well, let me clear that up first. We're going to be doing a survey just to see what the condition of the satellite is, and this will be after we've already berthed the satellite down onto the kick motor and we've actually backed the arm away and ungrappled it, and then we're going to do the survey from that point on. But no, there is no contingency prepared to bring back. The satellite itself would stick too far out of the payload bay to close the payload bay doors.
And I guess for Pierre or Bruce, you described an innovative and complex plan for the Intelsat. What in your minds is the most critical point of the Endeavour?
I'm sure we have two opinions here. Go ahead. I'm sure Pierre will talk about probably the most critical point is when he's attaching the capture bar. But as far as I'm concerned, I think Pierre's got that all watched. Seen him operate over there with a mass simulator and seen him work in the pool. So that to me isn't a big concern. To me, the biggest or the only that might get a little bit dicey for me is if in fact when Pierre, after he has installed the capture bar, has it hard docked, and then he goes to release it to drive the arm around and actually do the grapple. He releases the satellite with any roots on it whatsoever, then that makes my job a little bit tougher. Instead of going over and grabbing a stable satellite, then I'll have to do what we call a track capture and go over and grab something that's moving. But I have all the confidence in the world that Pierre's going to be nice and steady for me.
Well, those are my two concerns. One is, well, I think my heart rate's probably going to down quite a bit once Bruce grapples, and not because of Bruce's grab capability, but because I need to make sure I leave, as Bruce said, in a very stable position. And it's kind of hard over there in the simulator to get a good feel for. I guess I can come tell you at the post-flight whether or not it's like the mass simulator. I hope it is, but I'm not certain that it's going to be like that. So that, to me, is probably the most difficult phase of the flight is the bar installation and then the actual me stopping slow enough and nice and steady so that Bruce can grab it.
Question, with all your space constraints, I imagine something's going to have to be left off. Perhaps Dan or Rick could talk about anything that you're not bringing up that you usually would.
Well, I really can't think of anything. I didn't mention it earlier, but we're flying something called a MA, or mid-deck accommodations rack. Oriya was going to carry an experiment. However, some technical difficulties came up, and the experiment didn't get in time. So essentially that gives us a few extra lockers, so we can also use that rack lockers in. So we've actually, Rick talked about the extra cameras we brought, and we had a little space to bring the Linhof. We probably wouldn't have brought that otherwise, nor would we probably have brought the second camcorder. So we feel we have enough locker space. It's just, as Rick alluded to, when we take off all our launch and entry suits and get the EMUs out of the airlock and have 7 folks there, it's going to be kind of crowded, but we've made some little gadgets. We got some bungee cord that will help us hold the EMUs to the wall, and we've practiced stuffing things in the nook and cranny we can find. So we think we'll pull it off. I think it's safe to say that as we've gone from mission to mission, we're getting better and better at cramming more into the orbiter. We're learning how to do things, and just for this mission, we never tried putting 4 spacesuits in the airlock, and a lot of people didn't think it could be done. And there we have it. We've got 4 of them in there. It's tight, but it fits. In fact, somebody even won an award for proving that it could be done. And so, a lot of people have worked real hard at finding ways to fit things in the orbiter. And in addition, we each got to take a shirt and a pair of socks for a single day, so we're in good shape.
This is Jim Bank, Florida, Part 3. I guess for Dan or whoever wants to comment, yesterday Al Pennington used the words man in space at its finest in describing this mission. Given the irony of the Intelsat being bumped off Shuttle and then Shuttle going to rescue and all that, is this really NASA at its best in the 90s?
I'm not sure. I think so, but it's only a small part of NASA, and I think after the mission's over, you folks probably be the judge of that. But NASA is a big organization doing many things, and man in space is part of it, and we hope to prove that man in space is very viable and can do a very good job there, and we're trained and feel we can do that, and we'll have to wait till it's all over to see if it's true.
Let me ask sort of the flip of that question then. Obviously there's no good or worse mission that something could happen on something bad, but given that this is the maiden flight of Endeavour and a lot of exposure to that, and any thoughts on if there should be a bad day, what do we do next, and should we build another orbiter, and thoughts along those lines?
Well, I've always been a proponent of having a viable orbiter fleet, and realities being what they are, obviously no crew wants to have a bad day, but I think that the program's on regardless of what. It's a risky business, but we're doing an extremely good job minimizing that risk. And I think everyone here on this crew and everyone in the astronaut office recognizes that, and we accept that risk. And I think to a person in the office that if anything happened to us, we would not want it to be the end of the program.
Thank you. That's the questions we have. Do we have any other questions here at JSC? Just a minute, wait for the mic. Mark?
Mark Carruth, Houston Chronicle. Just a spacesuit question. Can you sort of describe what you would do with 4 suits if one of them had a problem and you couldn't use it? How do you plan to juggle your equipment around if you have to?
Who's the expert?
I'm the one with no backup. I'll talk about that. Tom can get in Rick's suit and Pierre's suit, so as a back, he can use either one of those. I think Pierre can get in Tom's suit. Rick and I are kind of the ones on the end, and he might be able to squash into Tom's, but out of luck.
They come in 2 pieces, you know. There's the hard upper torso, and then there's lower torso assembly. And Kathy and I don't have a backup set of legs for the suit, but I can wear Tom's upper part, and I think Pierre and Tom are completely swappable. Also, we can resize the arms a little bit. You know, we can adjust those, but it's a multi-hour task, believe it or not, to just the length of the arm.
We have a big matrix in our checklist, too, that says backups for crewmen, you know, for HUT, LTA, LCVG, all the components, even the carriers, go to if you have a failure.
Bottom line, just to follow up, there's still a good bit of the EVA work you could accomplish if that happens, say.
All of it. Yeah, all of it. In fact, it happens before we go out. We can get me out of my suit and get into Tom's fairly quickly. We don't have to resize anything. We just basically got to get me out, put me in the new hut, put the LTA on, gloves, helmet, and all stuff. Rick, similarly, if it happens while we're out there, unless the failure is the kind that we have to repress the airlock, we can, if there's not that kind of failure, we can just go hang on the wall in the airlock, and the other guy can get a lot of the work done. And if it turned out that we couldn't complete the day on that day, we'd button everything up for overnight and then go back out the next day with a better to finish it up.
Okay, Jim?
I'm reporting around for Air and Space magazine. I want to ask Dan and the rest of the crew, Dan, how you felt in the past when you've actually come rendezvous and caught the satellites, and how you expect to feel when you've caught this one.
Well, it's always a big relief after you've caught, because generally the rendezvous and capturing the satellite is a major objective of the given mission. So this one's a little different in that on this one we have a human between the vehicle and the satellite, so it'll probably be a little more. But and I think you know, relief and joy are probably the 2 things that come to mind when you successfully complete it.
Marcia Dennis, Associated Press. If things happen, would one person go out 3 days? Would that be allowed?
You know, in our mates, let's see. If something happens to Pierre on day 1, let's say Pierre just can't do EVA because we don't let him. We tie him up in the middeck and he'd go out. In that case, Tom and I go out on the day, and then Tom and Kathy go out on the 2nd day, and then Kathy and I go out on the 3rd day. So we'd each do 2, basically, and the same works for if something happens to me, Tom replaces me, and Pierre fills in that matrix where I would go. And let's see, if something happens to Kathy on the 2nd day, then I turn around and go out twice in a row. And then the 3rd day, instead of me going, Tom goes out twice in a row. And likewise, if something happens to Tom, I think the converse works. You go out in his place or something like that. But each person would do 2 EVAs is what it really comes down to, is each of the 3 of us would do 2 EVAs. If any one person, yeah. Does that make sense?
Yeah. But 2's the max.
2's the max that we plan to do. No, let's see. There's no requirement. Yeah.
I mean, we can cover all EVAs by having each of the remaining crewmen do 2 EVAs.
But there isn't anything anywhere that says we couldn't do 3, I don't think.
And that's pretty much would be a real-time call based on how the crew felt. They can speak to the physical exertion of the hands and the like working in the suit. And I think if for some reason, and you can see it's pretty far-fetched that we'd have to do one person do 3, I think that would be a real-time call.
Any other questions?